First, I want to thank the IEEE Control System Society for the honor and privilege to give the Bode Lecture. In this lecture, I will talk about snake robots. Snake robots are intriguing in themselves, and they also serve as a demonstration of the usefulness and power of nonlinear control theory. The motivation for our research on snake robots comes from biology, in particular from the mobility of biological snakes. Mobility is important for autonomous robots, and snakes can move in virtually any type of terrain, making snake robots suitable for rough terrains where wheeled or legged robots could run into problems. We here see how a biological snake moves in quite cluttered terrain, and instead of avoiding obstacles, it uses the obstacles, pushing against them to move even faster forward. Snakes are also very good climbers, and also here we see how it uses irregularities in the terrain to push itself forward. Snakes are excellent swimmers, and some snakes can even fly by climbing up to and jumping off branches and curling their body to glide through the air. So the mobility of biological snakes is what we want to capture in our snake robots. I will now present some of the research that we have done on snake robots, focusing on modeling, analysis and control. But first, a little bit about the background and how we came to do research on snake robots in the first place. What initiated this was a series of large city fires in Trondheim, the city of our university, during the period from 2002 to 2004. This led the fire department of Trondheim to sit down together with the research community to see whether we could come up with some new ideas for improving fire safety and making firefighting operations safer and more efficient. And one idea that came out of this was that of a robotic hose. The question that was asked was, why should the firefighters need to drag the fire hose into the burning building? Why couldn't the fire hose climb in by itself in advance, carrying a camera and other sensors, providing information to the firefighters outside, and thus creating a safer and more efficient firefighting operation? Technologically, the idea was that the high-pressure water inside the hose can be employed as a hydraulic medium for enabling the hose to move, as a fire extinguishing medium for the firefighting operation, and also as a cooling medium for cooling the robot in environments with extreme temperatures. To demonstrate this concept, Anaconda was developed. Anaconda was 3 meters long, weighed 75 kilograms and had 20 joints. It was the first water hydraulic snake robot in the world, and it was the biggest and strongest snake robot in the world, at least at the time of development. And Anaconda demonstrated the concept of a robotic fire hose, but it also demonstrated that there were a lot of research challenges to overcome when it came to controlling the robot, making it move forward and making it follow a desired path. To look deeper into these research questions, we developed ICO with electric motors, which made it much lighter and easier to work with. It only weighed 7 kilograms instead of more than 70. We here see how it curls up against these obstacles, just as the biological snake. It uses the obstacles, pushes against them to move forward. For a robot to be autonomous, it needs to be able to sense its surroundings and environment, and our next robot, Kulko, was equipped with contact force sensors behind the white and blue spheres here, making it able to detect obstacles and thus actively push against them in an efficient manner to move forward. But note in the videos that when Kulka runs out of obstacles, it is not able to move efficiently forward through undulations, and we will get back to this problem later. We have already seen that the main reason why sneak robots are so intriguing is their mobility. And this can, for instance, be useful for space exploration, as was investigated in a feasibility study for the European Space Agency. Here we see the sneak robot as a helper for the rover, where the sneak robot will be able to go into cluttered terrain and through narrow openings and into caves where the rover cannot go. The other reason, in addition to the mobility, why sneak robots are so interesting is that the sneak robot is a hyper-redundant robot manipulator arm which can transport itself. So you can equip it with a gripper or another tool in one or in both ends, and it can perform manipulation tasks. So space is one possible habitat for our sneak robots. Me personally, I'm equally fascinated by the oceans. The oceans are tremendously important to us. They contain food sources like fish and seaweed, they contain minerals that we need, and they contain a biodiversity which is crucial to maintain and which may, for instance, hold new cures to diseases. The oceans are also an important part of the Earth's total ecosystem and can provide us with important information about the state of the Earth, including climate changes. The oceans thus play a key role in addressing our global challenges stemming from an increasing population and the corresponding need for energy, food, and minerals, and for addressing the challenge of global warming. And yet, despite being so crucially important to us, we know more about the surface of the moon than we know about the bottom of our own oceans. Only 5% of our oceans have been explored. We need to get down there and explore to get more knowledge about what is happening and to utilize its vast resources in a sustainable manner, protecting biodiversity. So how do we get to the bottom? Although diving can be wonderful in itself, it can also be dangerous, and it is limited how deep divers can go. So ocean exploration therefore requires marine robots. For the last decades, we have had 3 types of marine robots available. We have survey AUVs, where AUV stands for Autonomous Underwater Vehicle, which are made for traveling long distances. These robots are torpedo-shaped to achieve good hydrodynamic properties, making them energy efficient. But as you can see, they do not have any manipulator arms, so they cannot interact with their environment, picking up a sample from the ocean floor, for instance. If we want to interact with the environment, we use ROVs, remotely operated vehicles. These are vehicles equipped with manipulator arms. The box-shaped carrying vehicle is not as hydrodynamically efficient as the survey AUV, so the ROV is better suited for short-range operations. In addition, the big box restricts access, and such an ROV is not able to access narrow spaces like, for instance, between rocks or inside ice caves. To gain such access, the ROVs are made smaller and smaller, but as they are made smaller and smaller, the arms that they can carry with them also have to be smaller and smaller, and in the end we are left with a pure observation ROV, which may look something like this. So this robot gives access to narrow spaces, but it has no intervention capabilities, no manipulator arms. So with these marine robots, we need to choose between a robot that can travel long distances, one that can interact with its environment, or another which can provide access to narrow spaces. Since our goal is accessing and exploring the oceans, it can be smart to instead learn from nature. We here see how sea snakes move efficiently through the water. Their body is long and slender, even more so than the Surveyor UV, and in addition it is flexible, able to move efficiently through the water and in between rocks and corals. And inspired by nature, my research group has made robotic snakes that mimic these sea snakes. We here see the snake robot, which we named Mamba, moving around in water. It performs these simple undulations just like the sea snakes, and we see how efficiently it then moves through the water. So, having looked at the background and motivation for our research, I will now present some of the research results on modeling, analysis and control. Snake robots are highly nonlinear dynamical systems. And when we started out, our conjecture was that model-based nonlinear control theory would have a lot to bring to the table of snake robotics research. So the first thing we did was developing a mathematical model of the robot, drawing as much information as we can from physics to understand the system and its dynamics in order to control it well. And some people asked, why do you need a mathematical model when you have a physical snake robot like Mamba? And this is of course because Mamba is one particular snake robot, and everything we can observe from its behavior, the only thing we know for sure is that this holds for the Mamba robot, while this mathematical model here can describe all the snake robots in the world, regardless of whether they are small or large, short or long, swimming or moving on land. So we use mathematics as a language to understand snake robots, and using nonlinear control system theory, analyzing this mathematical model, we can find inherent properties of snake robots and biological snakes, and in this way we use mathematics to decode the secrets of nature. And I think this is an important strength of control systems theory. Here are the configuration variables. The snake robot is a robot manipulator arm, so we have all the joint angles, that is, the angles phi between the consecutive links. In addition, the robot moves freely, so we also have the heading or orientation of the overall robot. This can be chosen in several different ways. It can, for instance, be the orientation of the head link, or, as here, the average of the orientation of all the links, theta bar. In addition, we have the position of the robot in the inertial frame, px and py, as configuration variables. We needed the mathematical model in a form that is suitable for model-based analysis and control design, and we thus developed a model which is in closed form, as opposed to previous existing models that included numerical evaluations of the hydrodynamic drag forces. And here is the model with some more of the matrices written out. For those of you who are used to working with models of robot manipulators, we can compare it to the robot manipulator model. This vector here, in addition to containing all the link angles, contains the orientation of the whole robot. And also, in addition, we have the dynamics of the center of mass. You will recognize some of the structure from models of robot manipulators, but in addition, we have hydrodynamic effects, including added mass, drag forces, and ocean currents coming into the model. For those of you who are used to working with marine vehicles, you will recognize the structure from models of other marine vehicles, but in addition comes all the link angles into the theta vector. And note that the matrices in the dynamic model here, they are quite a bit more complex, since this is not a rigid body like ordinary marine vehicles, but an articulated structure. And the link angles come in everywhere through theta in all the matrices. By removing the added mass and ocean current and replacing the drag forces with friction forces, the model describes snake robots moving on land. This is the resulting model of terrestrial snake robots. And chronologically speaking, this was of course the model that we started with. We first worked on terrestrial snake robots before we moved them into water and thus extended the model correspondingly. Having the model in place, we were ready to start analyzing the system. The first research question we asked was, how do we make a snake robot move forward? Again, we looked to biology. Snakes moving on land can use several different motion patterns, or gaits as they are often called, to move around. Lateral undulation is the most common one. But we also have sidewinding used by many desert snakes, concertina motion, which is typically used in very narrow locations, and rectilinear crawling, which is used by large, heavy snakes and also for snakes that are approaching prey. Swimming snakes use a combination of lateral undulation and eel-like motion. Lateral undulation is when the amplitude of the oscillation is the same along the whole length of the snake, while for eel-like motion the head is kept quite still and the amplitude of the oscillation increases towards the tail. So, nature suggests that an undulatory gait pattern is an efficient method for moving forward. However, remember Anaconda and also Kulko when it ran out of obstacles. They both try to use undulations to move forward, but they are pretty much stuck in place. Their center of mass does not move forward. To understand why, we went to the mathematical model to see which insights we could obtain from analyzing this. And using nonlinear analysis tools, we could derive several fundamental inherent properties of snake robots. First of all, the analysis showed that a feedback control law that asymptotically stabilizes a snake robot to an equilibrium point must be time varying. If time is not explicitly present in the control law function, then the snake robot cannot be asymptotically stabilized to an equilibrium point. And this supports the observations from biology that an undulatory gait pattern with a time-varying sinusoidal element can be efficient for locomotion. We then moved on to analyze the controllability properties of snake robots. As you know, a nonlinear system is called controllable if there exist admissible control inputs that will move the system between two arbitrary states in finite time. By investigating the equations of motion of the snake robot, we found that the snake robot moving on land is not controllable when the ground friction is isotropic. That is, when the friction coefficient is the same in all directions, and specifically when the friction coefficient in the sideways direction normal to the robot is equal to the friction coefficient in the lengthwise direction tangential to the robot. And similarly underwater. A snake robot swimming underwater is not controllable if the drag forces are isotropic. Given these conditions here, which are common conditions for slowly moving underwater robots, which snake robots are. So the friction cannot be isotropic if we want to control the snake robot, and that was the problem for both Anaconda and Kulko with their smooth surfaces. On the other hand, with anisotropic ground friction conditions, when the friction coefficient in the sideways direction is not the same as that in the lengthwise direction, then the snake robot becomes locally accessible, except from certain singular configurations, and these are when all the joint angles are equal. This is interesting since this result suggests that the joint angles of a snake robot should be out of phase during locomotion. This is a claim that had been stated in several previous works on snake robots based on simulations and observations of biological snakes, but here we see that nonlinear analysis is able to show this more rigorously. Knowing this, we took a closer look at the propulsive forces for the case of anisotropic friction. First, a little about the notation. We let xi dot denote the forward velocity of link I, and yi dot denote the sideways velocity of link I, and theta I is the angle that the link makes with the forward direction. For the special case, when the friction is anisotropic in the sense that the friction coefficient in the sideways direction is larger than the friction coefficient in the lengthwise direction, then the total force of the snake robot in the forward direction is given by the right-hand side here. This term, the first term here, is always negative, always opposing the forward motion of the robot. This term, however, can give a positive contribution, so it can provide forward motion. And note that this term is proportional to the velocity in the sideways direction, y dot. So it is the sideways link displacements that have the potential to propel the snake robot forward. Specifically, this term here is positive when theta is synchronized with the sideways velocity, like this, which it will be when the snake undulates. So the total analysis of the mathematical model supports using an undulatory gait pattern, but shows that this particular friction property here is required for undulations to make the robot move forward. Biological snakes have this friction property due to their scaled skin. And in water, the hydrodynamic drag forces provide this property also without these kind of scales because of the long, slender body of the snake. To investigate this further, we developed Wico, a snake robot with passive wheels for the sole purpose of creating the required anisotropic friction property. The passive wheels here have the same effect as the edges of ice skate blades. Pushing the skate blade sideways makes you move forward because the sharp edge gives the required high sideways friction and minimal forward friction. And with this anisotropic friction property of Wico, we see that lateral undulation produces forward motion. So both nature and the mathematical analysis suggest that we should use undulations to make our snake robots move forward, while making sure that the robot has the required friction property. Undulations are waves that propagate backward along the snake body, and this can be achieved by making each joint follow this reference signal here, where alpha is the amplitude of the joint motion, omega is the angular frequency, delta is the phase shift between the joints. Remember that the controllability analysis showed us that this phase shift is necessary to make sure that the snake robot is controllable. And phi O here is an angular offset that can be used to control the orientation of the robot, and thus the direction of the locomotion, and we will get back to this. Also remember that we saw from the mathematical model that it is the sideways motion of each link that makes the snake move forward. Moreover, we can observe from this illustration here that locomotion using undulation mainly consists of relative link displacements sideways with respect to the direction of motion. And this observation can be used to simplify the mathematical model, making it better suited for control design. The original model, although in closed form, is rather complex. The observation that we just made gives us a method for simplifying the model for the special case of undulatory locomotion. Instead of modeling the rotational motion of each joint, we model what is important for locomotion, namely the sideways displacement of the center of mass of each link. So the idea behind the simplified model is, instead of modeling the rotational joint motion of the snake robot, to model the sideways displacement, that is, the relative translational motion between the center of mass of the links. The model of the snake robot written in these new coordinates then looks like this. It is still not very simple, but it's simpler and better suited for analysis and control design of undulatory locomotion. The smaller the joint angles are, of course, the better this translational approximation of rotational motion is. And it has been shown through simulations and experiments that this control-oriented model here captures the behavior of the robot very well for joint angle magnitudes smaller than 30 degrees. That is, for oscillations within a 60 degrees range. So now we know that we can use an undulatory gait pattern to make the snake robot move forward, and we have a control-oriented model for analysis and control design of undulatory locomotion. We will use this general sinusoidal motion pattern, which we discussed earlier. And note also that we have introduced the function g to scale the amplitude along the length of the robot, so that this time-varying sinusoidal function can generate a broad set of gait patterns, including lateral undulation when g equals 1, and eel-like motion, where the amplitude of the oscillations are small near the head and increases towards the tail. This is achieved by making g for the head link close to 0 and let g increase for each link towards the tail. Based on the analysis so far, we had answered the first research question: which gait will make the snake robot move forward and under which conditions? Our next question was, how do we choose the gait parameters to move as efficiently and fast as possible? How does the choice of amplitude, frequency, and phase shift affect the forward velocity? If we increase the amplitude, will the snake robot move faster or will it move slower? And does the phase shift have anything to say when it comes to the forward velocity? To answer this, we plugged the gait pattern into the mathematical model. We used nonlinear averaging and were then able to show that the average forward velocity during undulatory locomotion is given like this. Here we see some of the parameters of the robot, like n, which is the number of links. The c's here are the friction coefficients, and vt is the velocity of the ocean current in the forward or the tangential direction. The really interesting thing is what we see here. Here we see that increasing the amplitude will indeed increase the forward velocity. The forward velocity is actually proportional to the square of the amplitude alpha, while the frequency and the forward velocity, they are directly proportional. And here we see that the phase shift does have an effect on the forward motion. Given the number of links n, we can choose the phase shift that gives the highest forward velocity by maximizing this function here. Specifically, by determining the optimal phase shift, we arrive at this graph here, which shows that the phase shift that optimizes the forward velocity varies with the number of links of the snake robot. So the more links the snake robot has, the smaller the optimal phase shift is, which makes sense. This simple graph is a useful tool when designing the undulatory gait pattern for a snake robot. And so are the direct relationships between the amplitude, the frequency, and the forward velocity. We then carried out simulations to verify the properties of snake locomotion that we had derived. The simulations were first performed with a simplified control-oriented model to verify the analysis, and then also with a complex original model in order to check the validity of the simplified model for this analysis. The upper plots are for 5-link robots, the middle ones for 10-link robots, and the lower plots for 20-link robots. The plots indicate that the average forward velocity along this axis is indeed maximized by the phase shift that maximizes k delta for the simplified model, and this optimal phase shift is shown by the red dashed lines. This also holds for the complex model, in particular for the SNCC robots with a higher number of links, 10 and 20, while for the very short SNCC robots with only 5 links, it is a little bit off, about 5 degrees. And here are the plots of the forward velocity for different values of the amplitude of the joint motion alpha. And the plots do indicate that there is a quadratic increase in the velocity as alpha increases. And finally, here are some plots of the forward velocity for different values of the angular frequency of the joint motion, the omega. And the plots indicate that there is a linear increase in the velocity as omega increases, which is in agreement with the theoretical analysis. To verify the results experimentally for terrestrial robots, we used WECO, which has 10 links. Here we see a little from our lab, which is equipped with a camera-based localization system, which allows us to measure the position of the robot. We ran several experiments for each value of alpha, omega, and delta, and the resulting velocities are shown as blue circles, together with a dashed line between the average of these velocities. Also, the experimental results support that there is a quadratic increase in the forward velocity as the amplitude alpha increases. There is a linear increase in the forward velocity as the frequency omega increases. And finally, we see that the phase shift that theoretically should maximize the forward velocity, shown by the green dashed line here, corresponds well with the phase shift that actually maximized the velocity during the experiments. So, using nonlinear averaging theory, we have found a direct relationship between the parameters of the undulatory gait pattern, the alpha, omega, and delta, and the average forward velocity. And this is very useful information for the control design of SNCC locomotion. We also verify the results experimentally for swimming SNCC robots. To the left, we see mamba swimming in a test tank using lateral undulations, where the amplitude of the undulation is the same along the whole body. While to the right, we see eel-like motion, where the amplitude of the undulation increases toward the tail and the head is kept quite still. And also these experimental results confirm the theoretical results. Having understood how to make the SNCC robot move forward and at the speed that we want, our next research question was, how do we make the robot not only move forward but go exactly where we want it to? In other words, how do we make SNCC robots follow a given path? In general, the motion of an underwater SNCC robot will be in 3 dimensions, as shown here. But for simplicity in the following, we will consider the 2D case, that is, the SNCC robots moving in the horizontal XY plane, either on land like WECO, or swimming as mamba. The same approach that we will now go through in 2D can also be applied in an extended form for 3D motion. We want the SNCC robot to move towards and follow this purple path. To achieve forward motion, we will use the undulatory gait pattern that we have discussed earlier. And now, to control the direction that the robot moves in, we will use the angular offset phi O. We use this simple proportional feedback control law shown here to control theta bar, which we remember is the orientation of the whole SNCC robot to a given reference value, theta bar ref. But what should this reference value be to make the snake robot move smoothly towards the path? To achieve this, we use something called line of sight control. This is actually what most of us do when riding a bike or a car or any other vehicle where we do not have the opportunity to turn on any direct force in the sideways direction. We can only steer the heading and the forward speed. What we intuitively do then is that we look towards the path that we want to follow, and we head the bike or the car such that it is oriented towards a point that lies a certain distance ahead of us along this path. This distance is called the look-ahead distance and is shown in yellow here. As we approach the path, this point, since it is always a constant distance ahead of us, will also move forward, and heading towards this point will give a smooth and steady approach towards the path. As we will see later, analyzing the mathematical model tells us that this look-ahead distance needs to be chosen sufficiently large, or else the system becomes unstable. And you may already have observed this from inexperienced bikers or drivers who look just ahead of the bike or the car, something which results in a wobbly, unstable behavior, while a good driver looks far ahead, has a long look-ahead distance. We will get back to this requirement on the look-ahead distance later. So we choose the reference angle to be the line of sight angle. Here Py is the shortest distance to the path, and delta is the look-ahead distance. Here we have implemented the line of sight path following control for Wiko. Initially, Wiko is heading away from the desired path, which is shown in black, and we see how it uses lateral undulation to move forward, and the line of sight algorithm makes it converge to the path. So the line of sight control law works well for terrestrial robots. At sea, however, there will be ocean currents, and using the line of sight approach, the currents will make the robot drift away from the path. What we need to do to avoid this is to set a crab angle, that is, to create an angle between the heading of the path and the heading of the robot. If this crab angle is chosen too small, the ocean currents will make the robot drift away. If the crab angle is chosen too large, the larger it is, the less hydrodynamically efficient the motion is. Just think of a ship moving sideways. It has to push away a lot more water than if it moves straight forward. And exactly the same holds for any slender marine robot. To address this, we introduce what we call integral line of sight, which looks like this. One way to interpret this formula is that instead of making the robot head towards a point that lies the look-ahead distance ahead of the robot along the desired purple path, we make the robot head towards the similar point along a displaced path that lies upstream of the desired path. Doing so will make the robot keep a crab angle, and the larger the distance, the displacement here, which we can recognize in the equation here, the larger this distance is between the desired path and the displaced path, the larger the crab angle will be. And to create exactly the displacement and thus the crab angle which is needed to make the robot stay on the path, we use the integral effect to automatically adapt the crab angle to the ocean currents, although both the direction and the magnitude of the currents are unknown. That the integral line of sight approach would work was a hypothesis, and to confirm this and also to check whether there were any conditions under which the approach would and would not work, we did a stability analysis based on Lyapunov theory. Starting out with the analysis, one problem was that all the joint angles in the phi vector here, They affected the unactuated sideways velocity of the robot. To handle this, we first introduced the coordinate transformation, where we shifted the position output of the robot from the center of mass, a distance epsilon along the tangential direction of the robot, to the location here, where joint angle motion does not affect the sideways velocity of the robot. This point is called the pivot point, and you can notice that in the lower equation after the transformation, the joint angle vector phi has disappeared from the sway dynamics. So, using the pivot point as our output, we have removed the direct effect that the joint coordinates have on the sideways velocity of the robot. We then use the integral line of sight formula as the reference for the robot orientation, as described earlier, but with this transformed cross-track error here. We still base the controller on the general undulatory gate pattern. However, we add some more dynamics to the directional control term. The outline term here in the middle corresponds to the proportional feedback control of the direction shown on the previous slide, while the remaining terms are introduced to give the closed-loop system, consisting of the snake robot and the controller, a cascaded system structure. And we use a feedback linearizing controller for the joint angles, which are fully actuated since we have motors at each joint. The resulting closed-loop system has this structure. The integral line of sight algorithm gives the desired heading of the robot, which is input to the heading controller, which gives the desired offset, and the gate generator takes this offset and, together with the chosen gate parameters, it creates an undulatory gate pattern, which is the reference to the feedback linearizing joint controllers of the snake robot. We also see this cascaded structure in the closed-loop system equations. The cross-track aerodynamics is perturbed by the heading error. The heading aerodynamics is perturbed by the joint angle error. And here is the aerodynamics of the joints, and this is a linear system due to the feedback linearizing controller. Using cascaded systems theory, it is possible to show that the origin of this closed-loop system is uniformly semi-globally exponentially stable, which implies that the cross-track error will converge to zero, and the orientation of the robot will converge to zero when there is no ocean current, and it will converge to the required crab angle when there is an ocean current. In other words, the path-following control objectives are satisfied. This is under the following conditions: that the look-ahead distance and the integral gain of the guidance law are chosen such that they satisfy these inequalities. As I mentioned earlier, the analysis shows that the look-ahead distance needs to be chosen sufficiently large, and how large depends on the maximum forward speed. The faster the robot moves, the longer the look-ahead distance should be. And this makes sense and probably agrees with your own experience when driving a car. Also, how large the look-ahead distance should be depends on the mass and maneuverability of the robot, given by the X and the Y parameters here, and also on the maximum magnitude of the ocean current. As is expected, the integral gain needs to be upper bounded to guarantee stability, and we here see that the upper bound is given by the difference between the minimum forward velocity of the robot and the maximum ocean current velocity. First, we did an experimental validation in the Marine Cybernetics Laboratory at MTNU, the MC Lab for short, where there is no significant current in the water. The desired path is approximately along the left line of lights, and we see how Mamba swims calmly towards this path and then follows it. It is easier to see how it follows the path in these screenshots of the experiment. Here the reference path is shown in yellow, and we see how Mamba swims towards the desired path and then follows it. And note that the robot's heading is parallel to the path since there are no currents in this test tank, so no crab angle is required. After these experiments in the MC lab, we flew both the robot and the personnel to Denmark, where we got access to the Hitzal's flume tank, where the theory could be tested with currents. In this experiment, we have told Mamba to follow the yellow path. We see how Mamba uses an undulatory motion to move forward, and it keeps a sufficiently large look-ahead distance such that it moves smoothly towards the yellow path. In this experiment, there is a current in the direction shown by the green arrows, pushing Mamba away from the path. And Mamba does not know which direction the current comes from or how strong it is, but through the position sensing, Mamba notices that something is pushing the robot away from the desired path, and the integral line of sight algorithm automatically adapts the swimming motion to compensate for this, making it keep a crab angle and thus follow the path. So, learning from nature, we have found a robot which moves efficiently through water, with a slender and flexible body which makes it easy to access narrow spaces like, for instance, between rocks, under ice, or inside shipwrecks. Mamba cannot stand still in water, however. It cannot hover. If it stops undulating, the ocean currents will make it drift away. The next research question I wanted to pursue was, why not combine the best from biology and nature with the best from technology, combining the slender and flexible body of snakes with thrusters, giving the robot the ability to hover, for instance to inspect something or to pick up a sample from the seafloor. We here see the resulting robot. This new bio-inspired robot combines several of the benefits of existing marine robots into one robot. It's like the Swiss Army knife for exploring the oceans. It shares the same advantageous hydrodynamic properties as the Surveyor UV, making it suitable for long-range transportation. Its flexible and slender body gives excellent access capabilities compared to even the smallest observation ROVs. And as it is a dexterous robot manipulator arm, it can interact with its environment, carrying out intervention tasks. So in this way we have moved from biology through university research, and in order to bring the snake robots out of the laboratories and into practical use, we have established a company called Illume. The name Illume is coined from the two words eel, due to its biological inspiration, and illume, which means to shed light on and gain knowledge, which is exactly what we want to do underwater. The Illume robot can be used as a subsea resident IMR vehicle. We have several man-made structures in our oceans, and it is important that these are inspected, maintained and repaired to pose as little disturbance to the ocean ecosystem as possible. The Illume robot is designed to live permanently at the seafloor, where it can safely operate 24/7 regardless of weather conditions. Since the robot does not require a manned surface support vessel as today's AUV and ROV operations do, its environmental footprint is minimal. Since the robot is available at all time, any problems that should arise can be detected and repaired much earlier. So the resident robot gives both greener and safer subsea operations. The robot can also move under and inside ice because of its slender and flexible body, and it can take samples since it can hover in water and use the tools at its ends to interact with the environment. The robot can also support aquaculture by inspecting the well-being of the fish and also the state of the nets, detecting and repairing holes to prevent fish from escaping. Here is the first generation Illume robot named Ely from 2016. Ely could swim down to 150 meters and could stay and operate at the seabed. Since our university is by one of the fjords of Norway, the Trondheim Fjord, we use this extensively for full-scale experiments, and I will show a short video describing the robot and its operation.
Until now, subsea inspection and maintenance has relied on underwater vehicles with surface vessel support. Illume changes everything. It's a new type of underwater intervention vehicle. The snake-like body combined with underwater thrusters makes the Illume unique. Flexible and dexterous for complex manipulation. Straight like a torpedo for long-distance cruising. Slender and agile for precision hovering and maneuvering even in strong ocean currents. And operating in confined spaces no other vehicle could reach. Snaking around obstacles and through narrow openings. Shifting into a U-shaped dual-arm configuration to tackle intricate tasks. Because the vehicle is modular, you can change combinations of joints, thrusters and payloads. You can mount different types of equipment, like torque tools, grippers, and various maintenance tools. Cameras along the flexible body give the operator a clear all-round view during inspection and intervention. Best of all, the Illume is engineered to live permanently underwater, where it can safely operate 24/7, regardless of weather conditions. This means less use of costly surface vessels and greener and safer subsea operations. With the intervention AUV of the future, Illume is reshaping underwater operations.
And here is the second generation Illume robot, Ely 500, which can go down to 500 meters. The Trondheim Fjord, which we use as test site for the Illume robots, is not as deep as 500 meters, but in this fjord we have demonstrated 1 month of subsea residency at 300 meters. Currently, Illume has cut the tether, demonstrating the next generation Ely, which is tetherless, which of course is a major benefit for subsea operations. And I will end this talk with a short movie showing how one Ely with a torque tool and another with a camera are planned to work together as janitors at subsea factories and beyond. So with this new bio-inspired marine robot, we are ready to explore the remaining 95% of our oceans. Finally, I want to acknowledge all the members of the SNEAK Robotics Research Group at NTNU, and also thank all co-authors from other groups for the great cooperation. Thank you, and thank you all for your attention.